Okay, and the next talk in the session will be given by Matthew Wilson, who's at Oxford and also Hong Kong. Yeah, is that correct?
Yeah. There's this HKU joint lab, so I don't.
Okay.
Yeah.
Okay, and he's going to talk about a diagrammatic approach to information transmission in generalized switches.
Great. Okay. Yeah. Thanks very much for the introduction. And thanks very much for having me here. It's a delight to be here. I hope in the future I get to meet you all in person as well. It's my first QPL. So today I'm going to be talking about some work my supervisor, or one of my supervisors, Giulio Kirabella, and myself have been doing on trying to get some intuition for how capacity activation works in the quantum switch. So our idea was to take a computation that's essentially done before, do some translating of it into diagrammatic languages, and see if we can use this to generalize what's going on. So that's very much the outline of the talk. We're going to rewrite the quantum switch, essentially just translate it into a sum of diagrams. We're going to use this to get a fun new intuition for capacity activation and use this to generalize some computations, some of which I still have no idea how to do algebraically. So part of this is just kind of an advert for this approach in computing these sorts of things. And of course, I'll give an outlook and some future directions at the end. So what is the quantum switch? So the quantum switch is a bipartite supermap. So it's something which takes in two channels, say channel 1 and channel 2, and it produces a new channel. So for example, here we've managed to produce some new output channel. There's all sorts of interesting supermaps, maps on channels, but one that's been the subject of a lot of discussion and has turned out to have all sorts of interesting properties is the quantum switch. So we can imagine, for example, taking two channels, and we can imagine a supermap which takes them and composes them in some particular order. Say it does 2 after 1. Or we can imagine a supermap which composes them in the other order. It does channel 1 after channel 2. And finally, we could imagine classically controlling which of these choices we do. But even further, you could imagine quantumly controlling this. So you could imagine, say, in control state 0, implementing one composition, in control state 1, implementing the other. And then you could imagine what would happen if instead I plugged in a plus state, a superposition into this thing. And then I could imagine that what I'd have is something like a superposition of the two possible sequential orders. Now, one of the interests in this thing is that it's an example of something with kind of indefinite causal order. Because the channels are both before and after each other, there's no way of saying who is first and who is second. Great. Okay, so that's the switch. Now, I know in talks you're not supposed to smash into a load of algebra too early on, but that's kind of the point of this talk, is that hopefully I can start with the algebra and ignore it for the rest of the talk. So how does the quantum switch look? The quantum switch of two channels, N1 and N2, with Krauss decompositions K1 and K2 respectively, can be split into 4 components. So all of these components kind of make intuitive sense. What we have is we have a control part here. So this is our control. This decides the order of the channels. So when the control is diagonal, when it's absolutely in state 0, it says, absolutely, let's apply channel 2 first, and then let's apply channel 1 first. In control state 1, it says, okay, well, let's do the other order. Control state 1 says to do channel 1 first, and then to do channel 2 first. But this is all stuff that you could do with a kind of classical control. The interesting stuff happens in the interference terms of the control. For example, when the control disagrees on the left and right-hand side which order should be applied, say 0 and 1 here, then on the left-hand side, the order corresponding to, so the order of channels corresponds to control state 0. We have channel 2, then channel 1. On the right-hand side, we have channel 1, then channel 2. And it's here where kind of some of the interesting stuff happens. And one of the super weird things that's been noticed is capacity activation of completely depolarizing channels. So a completely depolarizing channel is typically a kind of canonical example of a useless channel. It's something which takes an input state and ignores it, chucks it away, and always produces the maximally mixed state. So this is rubbish for communication. I can't get anything through it. Now, of course, sequential composition of depolarizing channels is also useless. However, it turns out that the superposition of their sequential compositions does allow some information through with some important caveats. So we can see kind of how this happens, or we can see this happen by really just computing one of these interference terms. It turns out that this expression here really does actually depend on rho. So rho makes it out to the other side, and this is pretty mad stuff. Now, rho only makes it out to the other side in the interference terms of the control. So if the receiver doesn't have access to the control, then the control is traced out. You lose the interference terms, and you don't get any capacity. So we've only got if the receiver also has access to this control qubit. So you can compute this output, but we wanted to know if we could get any more intuition for why this was happening. And we also wanted to try and find ways to coping with arbitrary permutations of n channels, because there's been work done on this sort of thing already, but going past kind of n equals 3, n equals 4 for depolarizing channels gets quite nasty. And I don't think anyone's done anything on kind of n equals 4 and above. So what are we going to do? Well, really, the idea was just to do a kind of simple rewrite into the kind of diagrammatic languages, which are pretty familiar to this field. So we're representing quantum states with wires coming out. We're representing completely positive maps, which would usually be represented in a Krauss decomposition, so a sum over Krauss operators like this. And essentially, we're taking this sum here and hiding it inside a wire. So this wire is secretly implementing the sum. And that's kind of a nice way to think about it when we're translating these off-diagonal terms. So first of all, just some clean notation. We're going to switch channel N1 and channel N2. And just to be clean, we just label this channel here by writing the CPM version of it and just labeling each box with the number 1, for example. So in this case, how does this diagonal term of the switch look? When the diagonal term, we apply channel 1, and then we apply channel 2. Okay, great. So we apply channel 1, then we apply channel 2. Simple stuff. It's just sequential composition. The interference term is a bit more interesting. So on the left-hand side, Krauss operator 2 is applied, and then Krauss operator 1. So 2, then 1. On the right-hand side, 1, then 2 is applied. So yeah, 1, then 2. And then there's dealing with these sums. So these sums, again, can be stored inside these wires that really, these wires do just tell us to sum over Krauss operators. So we've got a cute little picture for the output of the quantum switch. Really is just a translation. So the question is, what can we do with this? And what's nice about this is it makes this computation with depolarizing channels pretty immediate. So let's say we have 2 completely depolarizing channels. So we set channel 1 to be, so I should say what a completely depolarizing channel looks like. So depolarizing channel can be expressed by this following picture here. This is a trace. It chucks away the information that comes in, and it just produces this thing here, which is a maximum state. The important thing is that information can't get through this thing because the diagram separates in the middle. So again, sequential composition, of course, separates in the middle. There's no way to get from the bottom to the top. However, the kind of interfered composition looks pretty fun. So we take our expression for channel 1, which is this thing here, and we plug it in like this. And we plug in channel 2 in the same way. There's another 1 over D there. And we get this picture here. So absolutely, if we pull these wires straight, we see we really do get an identity channel. So that's cool. But also maybe we get a feeling for where the information is flowing in this thing. Of course, the depolarizing channel can be understood as something which takes the information and chucks it into the environment. Here, what we're seeing is, bearing in mind that these things represent kind of traces or the environment, the information from one side of the density matrix flows into the environment and via the environment to the other side of the density matrix. So this is kind of weird stuff, but it's kind of fun to think about. And if I get time, I'll talk a bit more about that later. So we've got a kind of new intuition for what's going on here. But what we've actually got is just, well, we've just computed an output that's already known. So there's a question of whether we can take advantage of this stuff to compute some things which we don't know how to compute yet. So, of course, the natural generalization is to look at n-party switches. So quantum controls of various permutations of as many channels as you like. So here I'm looking at various permutations of free channels, and I'm imagining, for example, in control state pi, we apply permutation pi to the channels. In control state pi prime, we apply permutation pi prime to the channels, etc. So again, we can talk about how this looks algebraically. We imagine some general control state in a superposition of all the possible permutations. We can look at the output of the switch, and the output of the switch again consists of a sum over all the kind of interferences between different permutations. And for each of these interferences, there's a kind of interfered composition of the channel. So this thing isn't strictly necessarily going to be a channel itself, but it looks a bit like one. Essentially, the Krauss operators on the left-hand side are permuted according to pi, and on the right-hand side according to pi prime. So this stuff can get kind of messy. So we'll think about how to write this stuff diagrammatically. And of course, what we do is we just order the Krauss operators and then join them up with wires. So let's say we have permutation on the left, which says pi1 is equal to 2, pi of 2 is equal to 3, and pi of 3 is equal to 1, for example. This tells us how to order the Krauss operators. So for example, here, we've written this kind of effective channel, and this is a particular one where we have Krauss operator 1, then 3, then 2. So that's what we've got here, 1, then 3, then 2. On the other side, we ordered them here, 2, 1, 3, 2, 1, 3, and we implement the sums by just joining these boxes up. Okay, good. So we can write down these more general interference terms too, and there's no problem dealing with any kind of permutations and number of channels that you like. Now, this is a cyclic permutation from the left to the right-hand side, and these turn out to have interesting properties. So if we track in the depolarizing channels, it takes almost no extra effort to see that this thing is still proportional to the identity. And in fact, because of this extra loop that gets created in the middle, we get the same normalization as in the quantum switch. Now, it turns out this completely generalizes. So one thing that we were really excited to see is that we could immediately prove that all cyclic permutations give information transmitting interference terms. So we can see this in this picture here. On the left-hand side, we have some indices, and on the right-hand side, we have some cyclic permutation of those indices. What this guarantees in the way around that we've cycled them here is that n is always going to be above 1 on the right-hand side, but 1 and n are going to be at the ends on the left-hand side. And this is enough already to show that this thing is information transmitting. So this is quite fun. So we just bother putting in this depolarizing channel and this depolarizing channel. We don't bother thinking about the others at the moment. And already there's a from the bottom to the top of the diagram. So we've already learned some pretty cool stuff about cyclic permutations, and it doesn't take too much work to convince yourself that there will also be a connection on the other side. So we really get an identity here. Okay. So yeah, and you get a load of loops, and it turns out that this always becomes 1 over d squared again. So moving from cyclic permutations, we wondered if we could characterize all of these interference terms and see which ones were kind of the best according to a kind of metric that I'll mention later. So the first idea is, okay, again, we can figure out whether this is kind of proportional to an identity or proportional to a depolarizing channel by essentially tracing our finger around the diagram and seeing where we end up. So here, because we end up back at the start, this thing is going to be proportional to a depolarizing channel. Now, it turns out that we can use these diagrams to compute a particular function. The details of the function don't matter, but we can write it down analytically, and it doesn't. And it's quite simple to write down. So how do we compute this function? So we compute a function by essentially iterating our finger around the diagram once. So we go down from some particular value a. All we can do is go across. All we can do is go up. All we can do is go across again. And then we kind of repeat from here. So we consider this to be one round of implementing the function c pi pi prime. Now, you can look at the properties of this function, and it turns out that it's quite an important function in the study of sortable or CDS sortable permutations. And the good thing about that is it means we can steal a load of results. So having found this condition that these pi and pi prime interference terms are depolarizing or information transmitting, depending on on whether or not they are sortable by things called CDS sorting algorithms, we're able to actually find some extra results. So noting that the normalization of any of these interference terms just comes from counting the number of loops that were in the diagram, we were able to show that the maximally normalized terms, which are proportional to the identity, are always cyclic permutations. So this for us is kind of a big deal, because what we were imagining was we want to find the protocol for supervising permutations that gives the maximal possible capacity activation. And we figured, okay, what's the heuristic for this? Well, we probably just want to increase the amount of row that ends up in our output state. And what do we mean by this? Well, let's have as many information transmitting terms as possible and have all of them maxed out on their normalization. And what we've shown is the unique choice to kind of optimize for those conditions is cyclic permutations. So we think now that these will be the best choices. And in fact, there's some evidence to suggest that this is true. This correctly predicts which permutations will be the best ones to superpose in the n=3 case, which has been studied algebraically. So that was pretty reassuring for us. And in fact, given this kind of intuition that these cyclic permutations are particularly good or interesting, you might just want to look at their properties on their own. And there's been 2 pieces of work on the properties of specifically cyclic permutations now, exploring the classical and quantum capacity advantages. Interestingly, if you have a big enough n, you start to be able to generate heralded quantum capacity as well as just classical capacity. Okay, so that's kind of, we've been able to do a load of computations and characterize a load of interference terms, a load of which we do not know how to do algebraically. So in terms of a tool, we're really happy with this method. It's been able to get us some results and allow us to figure out how to kind of optimize for our heuristic. There's also the kind of intuition side of things. And we mentioned this thing about information flowing through the environment. And we found if we actually didn't do the tracing out on depolarizing channels, so left them as their dilations, we're able to get even a bit more intuition for what was going on. So it's probably a bit bold to call this internal teleportation, but I thought it was a fun word. So let's imagine the dilation of a depolarizing channel. It takes the input state and chucks it into an environment, and it entangles the output with some other environment, creating a mass mixed state. So we can imagine taking the quantum switch of 2 of these dilations just on the input and output bits and not on the environment. And we can look at the interference terms. We can plug in our expressions for the channels, plug in some states, and kind of wiggle these diagrams to make them look a bit more appealing. And we end up with something like this. Now, we kind of think this could be quite an interesting picture, because if I try to say in words what's happening in the superposition, in one case, this input state here on the left-hand side, we know should get shunted into the environment of F, in particular, this first environment here. Now, we know from looking at the second, from the kind of right-hand side of this density matrix, that actually the environment of F1 should end up being entangled with the environment G2. But that's in state 1. So we have some statement about superposition 0, and we have some statement about branch of the superposition 1. Then back in branch 0, we also know that the output should be entangled with EG2. So we kind of think, okay, if only there was a way to say that this system really kind of is this system, then what we would have is explanation in words for how the state phi is correlated to the output. And of course, if I'm only interested in the output here, what would I do? Well, I would trace out. And this trace out here really does identify these 2 systems. It really connects these 2 versions of the environment and kind of makes them the same thing. So in the interference term, those kind of series of sentences we said really translate into actual maths. And we get a state that kind of teleports from one side of the density matrix to the other and to the output. So we thought that was quite a fun intuition for what's going on. Of course, one problem is it's like a completely basis-dependent intuition. We're looking at some kind of an interference term, which is kind of a weird thing to think about because it's not really an operation. An interference term is not a density matrix. But still, there's something appealing. The words that you might use to describe how this was happening do translate into maths. So that's the end of the talk. So I'll just briefly give a summary and outlook. We wrote down the quantum switch as a sum of diagrams, and we found two things. We got a really fun new intuition, which, I mean, for me personally, it makes me feel a bit more comfortable with what's happening in the switch. And I found it to be just kind of a fun intuition for the capacity activation. We also found that it was a really useful practical tool in calculating the output of the switch. And so there's an interesting stuff. Of course, we're not just referring to quantum mechanics stuff here. A lot of this is very structural. It's just cups and caps. We weren't even using any properties of boxes. It really is just wires. So how far does this go? Do we get capacity activation in various post-quantum theories? How general is this capacity activation condition? Okay. So yeah, can we characterize the output of input channels on of other input channels other than just depolarizing channels? And can we use these kind of sums of diagrams to get intuition for capacity activation in other supermaps, like superposition of channels? Finally, a lot of this looks a lot like what you do to compute not polynomials, like sums of these diagrams with loops and windings and stuff. And we found a kind of surprising relationship between that stuff and sorting conditions on permutations. So I just kind of, this is just kind of 4 a.m. thought. Maybe there's more stuff to be said there. I don't know. Is there other stuff already said about this? I don't even know exactly what I'm asking. Okay, so that's the end of the talk. Thanks very much for listening. I'd love to answer any questions.
Thanks, Matt. That was a really interesting talk. I've got a couple of questions.
Sure.
I've got 3 now. Oh, this is not sustainable. No, I've got 2. Okay, first one's from Pablo. Can you remind us quickly how much signaling is taking place between which parties exactly? I.e., whom of Alice and Bob holds the control qubit at which stage?
Yeah, great. Really good and important question. Thank you. So we're assuming that Alice does not have access to the control qubit. So we have a kind of this super operator, this switch already exists as a thing that has had the plus state plugged into it. And Alice doesn't have any access to this control bit at all. However, the control and the output of the channel are both sent to Bob. So Alice sees input of N1 and N2, and whichever one is kind of in front of her. And Bob sees outputs of these two plus the control. So, and there is only signaling between this input and these two together. If you ignore either the outputs or the control, there's no signaling. Yeah.
Okay, thanks. Second question is from Alex, and it's when you say cyclic permutations are optimal, does that mean generalized switches that sum over all cyclic permutations give maximal capacity on depolarizing channels?
Yeah, so let's say, I guess, yeah, I mean, so first of all, we don't have a proof that in general this will give the maximal capacity activation. We just have this heuristic that it really feels like if you want to maximize capacity activation, you want to increase the amount of rho that's knocking around in your output state. In terms of that heuristic, whether they're optimal or not, so they are in the sense that let the number of orders that I'm choosing be anything less than the number of channels. Then I have at least I could at least choose all of these permutations to be cyclic, because there's n cyclic permutations, kind of mutually cyclic permutations, and I've got either n channels or less. In that case, it's absolutely true that for our heuristic, this thing is optimal in the sense that if I tweaked any of the channels so that they weren't all mutually cyclic, we'd have at least some interference terms that were either not proportional to the identity or didn't have the maximal possible normalization. Actually, just to clarify, so in terms of these interference terms, the only ones that are information transmitting that have maximal normalization are cyclic permutations. And we're able to prove that using this correspondence with CDS sortability.
Okay, thanks. There's a third question from Pierre Manuel. That is, can you remind us why you want to retrieve that 1 over d squared normalization rather than 1 over d to the n for n parties? Is that because of the maximum capacity that can go through a depolarizing channel?
Yeah, so our intuition is essentially we're going to have some kind of an output where we've got all sorts of interference terms in the control. You know, you might have, well, in general, I'm going to have all sorts of interference terms. Imagine some general term between pi and pi prime. And if this is information transmitting, so if the channel that it comes with, this pi prime thing, if this thing is proportional to the identity, then I want to make it as big as possible. And so that's why I'm looking for the things that are proportional to 1 over d squared rather than the things which are anything less than that. So essentially, you want to get something which is proportional to the identity and has as many loops as possible. Okay. Each one contributes a factor of d.
Okay, cool. I had a quick question about, can you give some intuition why the CDS algorithms pop up? I'm trying to remember, it's context-directed swap, right? So yeah, just maybe give some intuition for me to help my memory.
Yeah, sure. I'm not sure if I can actually. Let me see. It was a little while ago. So I actually could not reel off the intuition at all. But I'm really annoyed. I actually dropped the reference when I was editing this minute, so it's not there. So I'll drop the reference in the Slack channel. And I'll maybe even comment it on the YouTube page as well, because it'd be nice to have it there. And they actually show in their paper that finding whether things are CDS sortable is equivalent to some problem, and it turns out the problem they end up trying to solve is R1. But I can't remember how they make their steps. Okay,
cool. All right. So I think I'm gonna put a clap again, and I'll do one in real life, but I'll put a clap there. And also,
it's very much enjoyed.
If I make it close to the mic, it sounds more impressive. Anyway,
yeah, it does actually. Although because there's less of an echo, it almost sounds more lonely. It almost sounds like more claps if you're as far away as possible.
But I want to take this opportunity to actually thank you, because you've been the main tech of the joint QPL MFPS workshop, and I think you designed, architected everything, you tested the solution. So it's been but the reason why all of this has worked is because of your efforts. So I'm going to clap again.
Thank you very much.
Allow anyone to put any emoji in the Slack channel to show appreciation. I don't care if it's a sea of applause. Just like fill the Slack channel with emoji.
I wish I'd made that one into an emoji now. Can I just say though, it's absolutely not just me. Like, there's been a team of us, and we've been working. Yeah, we have been working really hard, but loads of other people have also just been like putting in a super amount of effort. So yeah, thank you very much to all of you, to all of us. Yeah, but thanks very much.
Thanks. Okay. And I think we're going to move on to the next talk, hopefully.
I can't wait.
Or should I say performance?
Yeah.
There is some really great emoji coming through on the Slack channel. Okay. Thanks again, Matt. All right. Take care.
Brilliant. Thanks so much.